Hello students, in our last class we have discussed conductance of electrolytic solution, and in conductance of electrolytic solution we have discussed specific conductivity, molar conductivity, and then variation of specific conductivity and molar conductivity for both strong and weak electrolytes. And then we have seen that the limiting molar conductivity of strong electrolyte can be determined from the graph, but for weak electrolyte we cannot determine the limiting molar conductivity from the graph, since the graph was an exponential graph. Okay, and we have get that the limiting molar conductivity of weak electrolyte can be determined by using a law, and that law is Kohlrausch law of independent migration of ions. So today we will discuss the Kohlrausch law of independent migration of ions. Okay, and according to this law, the limiting molar conductivity of an electrolyte is always equal to sum of limiting molar conductivity of the individual cation and anion. Suppose we have an electrolyte AB, and the electrolyte when dissociated it gives A positive and B negative. Then according to Kohlrausch law, lambda m naught for AB is always equal to lambda m naught for A positive plus lambda m naught for B negative. That means the limiting molar conductivity of an electrolyte is always equal to sum of limiting molar conductivity of the individual cation and anion. Okay, for example, suppose we have the weak electrolyte acetic acid, and when the acetic acid will dissociate it, then it will give acetate ion, okay, acetate ion and H positive ion. And then according to Kohlrausch law, the limiting molar conductivity for acetic acid is equal to sum of limiting molar conductivity of the acetate ion and the limiting molar conductivity of the H positive ion. Very simple law, and by using this law we can determine the limiting molar conductivity of a weak electrolyte. Okay, so now we will determine the limiting molar conductivity of acetic acid from some given data, and we will solve a question, and the question is calculate the lambda m naught for acetic acid CH3COOH from the following datas. We have some datas, and given that lambda m naught for HCl is equal to 426 Siemens centimeter square per mole. Okay, and then lambda m naught for sodium acetate is 91 Siemens centimeter square per mole, and then the lambda m naught for sodium chloride is 126 Siemens centimeter square per mole. So we have to determine the limiting molar conductivity of acetic acid from these data. Okay, so we know according to Kohlrausch law, lambda m naught for acetic acid is equal to sum of lambda m naught for acetate ion and lambda m naught for H positive ion. Now from the given data we will find where the acetate ion is present. In the second data, that is lambda m naught for sodium acetate, the acetate ion is present. That means when the sodium acetate will break or dissociated, then acetate ion and then Na positive ion will form. Okay, so for acetate ion we will put lambda m naught of sodium acetate. Okay, and then we have to put the value of H positive ion, and for H positive ion we will put lambda m naught of HCl, lambda m naught of HCl. But now when we are putting the values of acetate ion and H positive ion, then we get extra Na positive and Cl negative ions. Okay, so to get the exact value we will minus or we will subtract the lambda m naught for sodium chloride. So like acetic acid, we can break the limiting molar conductivity of sodium acetate, HCl and then sodium chloride, and after cancelling we will get only the lambda m naught for acetate ion and then lambda m naught for H positive ion. So now we will put the values, and the lambda m naught for sodium acetate is 91. Okay, after that the lambda m naught for HCl is 426 minus the lambda m naught for sodium chloride is 126. They all have same unit and the unit is same in centimeter square per mole. So after calculating, the answer is 391 same in centimeter square per mole. So by using Kohlrausch law of independent migration of ions, we have determined the lambda m naught or limiting molar conductivity of acetic acid, which is a weak electrolyte. Okay, these are some strong electrolytes, their values can be determined. Okay, but from them we have determined the limiting molar conductivity of acetic acid. Okay, so by using Kohlrausch law of independent migration of ions. So this question is a common question for exam purpose. Okay, so we have seen the application of Kohlrausch law. Again we will solve another question, and the question is calculate the molar conductivity of silver chloride at infinite dilution. And molar conductivity at infinite dilution means the limiting molar conductivity from the following data. Okay, at first the lambda m naught for silver nitrate is given as 13.0 0.34 Siemens meter square per mole. In this case, the unit is changed. Earlier it was Siemens centimeter square per mole, but now the unit is given in Siemens meter square per mole. And then the lambda m naught for KCl is given as 14.99 Siemens meter square per mole. Okay, and then the lambda m naught for potassium nitrate KNO3 is given as 14.49 Siemens meter square per mole. Siemens meter square per mole. So we have to determine the lambda m naught for silver chloride, and according to Kohlrausch law, lambda m naught for silver chloride is equal to lambda m naught for Ag positive and plus lambda m naught for Cl negative. That means the limiting molar conductivity of an electrolyte is equal to sum of limiting molar conductivities of individual cation and anion. Okay, now we have to find the term having a Hg positive ion. So in the given data, Ag positive is present in the first one. Okay, so we will put lambda m naught for AgNO3. Okay, then we have to find Cl negative. So Cl negative is present in second data. That means lambda m naught KCl. Okay, so now we have some extra terms, that is NO3 negative and K positive. So to cancel them, we have to minus or we have to subtract the value of lambda m naught for KNO3. Okay, so when we will break them, the final result will be this one. Okay, now we will put their values. The value of lambda m naught for AgNO3 is given as 13.34. okay, then for KCl the value is 14.99. okay, and then minus for KNO3 the value is 14.49 and the unit is same for them and the unit is Siemens meter square per mole. So after calculating, the answer is 13.84 Siemens meter square per mole. So we have determined the limiting molar conductivity of silver chloride from the given data using Kohlrausch law of independent migration of ions. So earlier we have determined for acetic acid. So now we have determined for silver chloride. Okay, so now we will study another application of Kohlrausch law, and using Kohlrausch law we can determine the degree of dissociation, that means alpha, for a weak electrolyte. So about degree of dissociation you have learned in class 11 chapter number 8, that means the ionic equilibrium. Okay, so suppose we have lambda m naught which is equal to limiting molar conductivity of a weak electrolyte. Okay, then again we have lambda m, that means molar conductivity of the electrolyte. lambda m naught is limiting molar conductivity and lambda m is molar conductivity for the same electrolyte, then the degree of dissociation alpha is equal to lambda m divided by lambda m naught. That means when we will determine the ratio between molar conductivity and limiting molar conductivity, that ratio will give the degree of dissociation alpha of the weak electrolyte. So the another application of Kohlrausch law is to determine the degree of dissociation for weak electrolyte. Determine the degree of dissociation for weak electrolyte. So this one is another application. So using this formula, we can determine the degree of dissociation. So when we have the degree of dissociation, then we can again determine the dissociation constant for weak electrolyte. Okay, suppose we have the weak electrolyte acetic acid CH3COOH, and we know the weak electrolytes do not dissociate completely. That means the acetic acid will dissociate it to give acetate ion and H positive ion. Okay, but in the solution acetic acid will also present and equilibrium is established between the undissociated acetic acid and the dissociated acetate and H positive ions. Okay, suppose initially the concentration of acetic acid is C, and initially since the acetate ions and H positive ions are not formed, therefore their concentration is 0. Okay, now at equilibrium, suppose C alpha amount of acetic acid is dissociated. So from the equation we have seen that 1 mole of acetic acid is giving 1 mole of acetate ion and then 1 mole of H positive ion. So when C alpha amount of acetic acid will dissociate it, then the amount of acetic acid acetate ion formed is C alpha, and the amount of H positive ion formed is C alpha. One is giving 1 for acetate ion and 1 for H positive ion. Therefore, when C alpha will dissociate, then the amount formed is C alpha and C alpha. Okay, thus the dissociation constant Kc equal to, we know the ratio between product of concentration of product and the reactant at equilibrium. Okay, so for acetate ion the concentration is C alpha, for H positive ion the concentration is again C alpha, and in this case the concentration is C minus C alpha. So when we will take C as common, then the result is C into 1 minus alpha. Okay, and then one C will cancel with another, and the result is C into alpha square, C into alpha square divided by 1 minus alpha. So when we will determine the value of alpha, that means the degree of dissociation from Kohlrausch law, and when we have the initial concentration of the electrolyte, then we can also determine the dissociation constant of the weak electrolyte. Okay, so we have studied two applications of Kohlrausch law. So the first one is to determine the limiting molar conductivity of a weak electrolyte, and after that the second one is to determine the value of degree of dissociation for weak electrolyte and then the value of dissociation constant from the known value of degree of dissociation. Okay, so now let us solve a numerical related to degree of dissociation. Okay, so the question is the conductivity of 0.00241 molar acetic acid is 7.896 into 10 to the power minus 5 Siemens per centimeter. That means the conductivity is given or the specific conductivity is given and the value is conductivity kappa equal to 7.896 into 10 to the power minus 5 Siemens per centimeter. And the concentration is also given, C is equal to 0.00241 molar equal to 0.00241 mole per liter. Okay, molar means mole per liter. Now we have to determine the molar conductivity. So we know lambda m, that means molar conductivity equal to kappa into 1000 divided by m. Okay, and the value of kappa is 7.896 into 10 to the power minus 5 Siemens per centimeter into 1000. Okay, divided by m, and the value of m is 0.00241. And in our last class we have discussed that when we will multiply 1000, then the unit will change to mole per centimeter cube. Okay, so after calculating, the result is 32.76 Siemens centimeter square per mole. So we have determined the value of lambda m, that means the molar conductivity for acetic acid from the given data. Okay, now we have to determine the limiting molar conductivity. Now we have to determine the degree of dissociation, and to determine degree of dissociation we need the limiting molar conductivity, and the limiting molar conductivity of acetic acid is 391 Siemens centimeter square per mole. Okay, so we have already determined the limiting molar conductivity of acetic acid in earlier one problem. Okay, so from that value in the question, the limiting molar conductivity of acetic acid is given as 391 Siemens centimeter square per mole. So now we will determine the degree of dissociation. So we know, again we know for the second part, degree of dissociation alpha is always equal to lambda m divided by lambda m naught, and the value of lambda m we have determined as 32.76 Siemens centimeter square per mole, and the value of lambda m naught is given as 391 Siemens centimeter square per mole. So after calculating, the result is 0.0839. So we have determined the degree of dissociation for acetic acid from the given values of lambda m and lambda m naught, that means the molar conductivity and the limiting molar conductivity. So the next topics were electrolysis, electrolytic cell, laws of electrolysis, but those topics were deleted from the new syllabus. Okay, so in our today's class we have completed the chapter electrochemistry. We have learned the Kohlrausch law of independent migration of ion and then application of Kohlrausch law of independent migration of ion. So in next class we will study unit 12, that means aldehyde, ketones and carboxylic acid. That's all for today's class. Thank you.